Scholars, Ms. Perez here again, coming to you live from the orchestra that's in my living room. Just kidding. I wish I had an orchestra in my living room. I wish I had musical instruments with me too to play right now, but unfortunately I don't. Anyway, today we are going to be investigating how sound is affected through wind and string instruments, hence the background. So let's start with that. I will share my screen with you as we normally do. So the three tabs that you should have open are your Google Classroom, the classwork document that you got from Google Classroom, and then the Simplicity of Science website. I'm going to add some links here for some really cool demos that are related to sound that we're not going to be able to talk about in class today, so keep an eye out for those as well. Okay, so let's start with our lesson. Okay, so today we are going to be investigating wind and string instruments. The materials you need for today are your notebook, pen, and pencil. You don't really need a calculator for today's lesson, and then you'll need the three tabs open that we had before. Okay, so throughout this unit, we've been talking about different properties of waves and how that affects the sound that we hear. So today we're going to talk about how that relates to string and wind instruments. So we're going to gather evidence through a series of videos, not really an investigation, and relate how the length of a string or the air column of an instrument affects the sound that we hear. Okay, so for today's Do Now, I'm going to play two different clips. One will be of a flute solo and the other one will be of a piccolo solo. Take note of the difference between the two instruments in the classwork document that you have. There's a section on the top that says Do Now, so write your thoughts there. Okay, so as you're watching this video, keep in mind the sound that you're hearing and also the shape of the instrument and what the little girl is doing to create the different sounds in the instrument. We're just going to pause here, so take the next few seconds to finish wrapping up your thoughts on what you observed. Okay, let's move on to the video. Okay, so this video here is a woman playing the piccolo with an orchestra in the back. Okay, we're just going to pause there. So take the next few seconds again to finish wrapping up your thoughts on what the difference is between the piccolo and the difference between the flute. Both in what you heard and then also what you saw in terms of the shape and the finger movements of both women who were playing. Okay, let's move on. So we are going to discuss the results of the do now at the end of class. So whatever you're writing down, if you have any questions or you're unsure of what the difference is, it will become clear later on. So just keep your thoughts and your predictions in the forefront of your mind as we continue to discuss today's lesson. Okay, so before we are able to fully understand what's going on in wind instruments, we have to understand first the concept of a standing wave. So we haven't really talked about that yet. So we're going to watch a video from Bozeman Science where he's going to lay out for us what a standing wave is, and then he's going to discuss what nodes and antinodes are. These three words are very important for us understanding what's going to be laid out throughout this unit, throughout the rest of this lesson, and also tomorrow's lesson. So take a note of these three words in your notebook. And as we're watching the video, keep them in mind so when you hear him talking about them, you can press pause and write down the definitions. Also, in your classwork document, there is a section for you to write video notes on this video. So keep that up as you're watching video. Write down any key points or any things that you might find interesting. Okay. We're going to watch the whole thing. If you need to pause it to write down any definitions or any key points as he's speaking, then you can do that.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 115. It's on standing waves. Standing waves are like they sound. They're waves that appear to stand still. And so an example of a sound standing wave is the waves found inside a vuvuzela. And so you blow on it, you get that sound. You blow it with a higher frequency, and then you could even try to pierce your lips a little bit more and get an even higher frequency. But what's happening is you have these specific standing waves that sit within the chamber of the vuvuzela. Now, a wine glass works the same way. If you rub your finger with a little bit of water around the surface of it, what you can do is generate these standing waves inside the wine glass. What you're doing is vibrating the sides, and as you do that, you're vibrating the air, and since you have a standing wave inside there, it makes this pitch. Add water to it, and you're going to have a slightly different pitch. And so waves can either be traveling or standing waves. Traveling waves will move from one place to another, and standing waves will appear to stand still. Now, when you look at it, it's kind of an illusion. They're standing still, but the traveling waves are bouncing back and forth. In other words, they're being reflected off the boundaries, and then there's interference to create these standing waves. And so if we look at this animation, the dark wave is going to be the standing wave, but in the background you can see the blue and the red waves that are bouncing back and forth, and it's the summation of them that creates the standing wave. Now, if you notice, that standing wave is going to have areas where it's not moving at all, and that's due to destructive interference, where the waves are canceling each other out, and we call those in physics nodes, areas where it's not moving. And then we're going to have total constructive interference in certain areas, and we call those antinodes. That's where it's moving the maximum amount back and forth and back and forth. And so an example of this could be found in instruments, for example. So a string instrument is going to be fixed at either end, and this animation is a good example of that. It's fixed on either end, and as the waves bounce back and forth, you create these standing waves. If we shorten that, like on a guitar, then we can get different pitches. A tube is going to be the same way. A tube could be open on both ends like a flute, or it could be closed on one end like a vuvuzela, and that's going to create these standing waves as well. So let's start with traveling versus standing waves. And so this PHET simulation, I'm generating some waves. Those waves, and this is just kind of theoretical, are moving out the door, and then they've moved on forever. But if we add a boundary on the other side. In other words, if we add a fixed boundary, you can see now there's a reflection back. So those waves didn't just keep going, now bounce back, and now they're going to bounce back again. And as that wave goes back and forth, you can see that we're starting to generate these standing waves. And you can even see those nodes and those antinodes. In other words, those areas where it's not moving and those areas where it's moving quite a bit. So this is an animation of standing waves. And so what we're doing is as the blue wave moves to the right, becomes the red wave, which moves back to the left, and it just keeps going and going and going. We're getting destructive interference. That's causing these nodes where they cancel each other out. And then we have constructive interference, and that's creating these antinodes, where those two waves add together to make a much bigger wave. Now, an example of this, if you've ever played baseball before, when you hit the ball, sometimes you'll hit it and the bat will kind of buzz in your hands. In other words, it vibrates quite a bit. And the reason why is that you're hitting the ball on an antinode, an area where the waves going up and down the bat are actually constructively interfering to create a huge vibration there. And we refer to it as the sweet spot, the spot on a bat where the node is, where you don't have much vibration, that you hit the ball and you don't feel really any vibration at all. And so let's go through experimentation. So this is a sim bucket simulation. What we're doing is looking at standing waves. The first one we're going to look at is when you have two fixed ends. So an example of this could be a guitar. And so what you do is you have a string, you hold it on one side, and then you pluck it, and you're going to have vibration. So what do you get? Waves going back and forth and back and forth. What's the standing wave then? The standing wave is going to be that green wave in this simulation. It's that wave that is the addition of the other waves. What's interesting in a guitar is that you don't only have one, what we call harmonic, or one standing wave, but you can have multiple standing waves. Now, in all these standing waves, what makes them the same is that we have a node on either side. In other words, there's no net movement on either side of that string. If we look at an instrument like a tuba or a vuvuzela, what is the characteristic of that? Well, we're vibrating it, but you can see that on the left side we have a node. It's not vibrating, but we have an antinode at the right side. So in each of these harmonics, the left side is going to be a node. It's not going to move at all, but the right side is going to be an antinode. And so we still have those traveling waves going back and forth and back and forth. It's just that one of those ends is free to create an antinode, and then we just have reflection off of that end. These are all the different harmonics. What keeps them all in common is the node on the left, antinode on the right. If we then look at something that has two open ends, like a flute you don't blow in one end. You're blowing on the top to create the vibration, or a pan flute would be an example of that. And so what's going to create the standing wave here? Well, in this first harmonic, we have the node in the middle, and then we have antinodes on either side. Now we have two nodes near the middle, antinodes on the side. So what's the characteristic of a standing wave in a chamber that has two open ends? It's always going to be an antinode on either side. But depending on the frequency, we can get different pitches as we blow through. Rubens tube is a really cool example of that. In a Rubens tube, what you do is you fill up a chamber with gas, a gas that's flammable. And so this guy's lighting the chamber. So we were having flames coming out of the top. But on a Rubens tube, you put a speaker on the side. And what that speaker does is create these longitudinal waves. Those longitudinal waves, as they move through, will create areas where there's a lot of compression. And an area where there's a lot of compression or antinodes, then the gas really can't make its way out. And so it'll be really low there, but at the nodes, it'll actually come out quite a bit. And so did you learn to predict the properties of standing waves? They result from reflection of these traveling waves. Could you collect data? Again, I use a sim bucket simulation to do that. And then finally, could you describe examples of when this occurs, standing waves? Musical instruments are good, baseball bats are great, and I hope that was helpful.
Okay, scholars, I also hope that was helpful. So make sure you can take the next minute to finish wrapping up your thoughts on your classwork document about this. We're going to, if you didn't get a chance to write down the definitions for those 3 words that we had at the beginning of the video, we're going to come back to that now. So a standing wave, as I'm reading these, please make sure you write them down. A formal definition for a standing wave, also known as a stationary wave, is a wave which oscillates in time but whose peak amplitude does not move in space. So what that means is that, again, like the wave is going back and forth, up and down, but the wave isn't moving left or right. It appears to be standing still. Okay, and then move myself down here. And then we have a node and antinode. The node is the position on the wave that appears to be stationary. So these points here are the nodes. So you think about it as like no movement is where the nodes are. And then the antinode is the position of the wave where there is a maximum amplitude displacement. So over here, the wave is going to be oscillating up and down. So that will be our antinode. Just take the next few seconds to write this down into your notes. If you need to press pause to make sure you get them in a notebook, then please do that now. Okay, so we are going to watch one more video to connect everything we've learned to how organ pipes work. So this is a demonstration with organ pipes. So when we did the investigation in lesson 1 of this unit, we played around with how changing the length of the string affects the pitch of the string. In this demo, we're going to see how changing the length of our tube is going to change the pitch of the sound that we hear. Okay? So in your classwork document, there is another section for video notes. Again, write down any key points you may hear and also anything that you might find interesting.
Okay, this is a demonstration of organ pipe modes of vibration. You may already be aware that a longer organ pipe, this is open on one end, and also open on the other end, and this is where the air is introduced. Then there is a knife edge made out of wood that the stream of air goes through this hole against the knife edge, and then there's an instability when the air is incident on a knife edge. This instability will cause a puff of air to come out outside of the pipe and then a puff of air to go inside the pipe, alternating outside and inside. And there's a particular frequency that's associated with this instability. And if that frequency matches the length of the pipe, then you'll get a resonance in the pipe. Like that. If you move to a shorter pipe, it's built the same way. The length is shorter. You get a higher sound, and even shorter. You can, if you blow hard enough in here, force different modes to sound in the pipe. What we were hearing just then is the fundamental mode, the lowest possible frequency that this pipe will produce. But any pipe actually produces a sequence of frequencies that follow at least approximately the harmonic series. So this is the fundamental, the lowest possible frequency. If I blow a little harder, I get a mode that, for those of you that have a musical background, will recognize as approximately an octave above it. Do the same thing on this one. So we get a lower mode, a higher mode, and then there's actually an infinite sequence of these modes that goes up to infinity, and that gives the organ pipe its character, its characteristic sound. As I mentioned before, all of these pipes that I've shown you so far are open on both ends. If you ask what happens when you close one end, and I'm just going to put my hand across it to close this end, then, well, first I'll do it with it open, then close it. So you'll notice that the sound is lower. In fact, if you ignore end effects, then the theory predicts that the sound is actually 1 octave lower, the frequency being half of its original value. That is the reason why a clarinet sounds lower than a flute does. flute and clarinet both have about the same length. The flute is open on both ends, but the clarinet, the mouthpiece end, is effectively closed. And so the lowest notes you can produce on a clarinet are much lower than the notes that you can produce on a flute. That's organ pipes.
Okay, I hope you guys found that video interesting. So take the next few seconds to finish wrapping up your thoughts on what we just observed.
Okay.
Okay, so after watching all these videos, we should have arrived at these key points. Please write these down into your notebooks. Right. The first is decreasing the length of a string in a vibrating string decreases the wavelength. This increases the frequency, which results in a higher pitch. Again, this relates to the investigation that we did at the beginning of this unit. And you can connect that also to when you're playing guitar. If you hear as your finger gets closer, closer and closer to the smaller frets, then you hear the pitch. Like when your finger cuts the string in half, then you start hearing lower and lower pitches. Higher and higher pitches because the length of the string has been shortened. The next one is decreasing the length of a vibrating column of air decreases the wavelength. This increases the frequency, resulting in a higher pitch. So this relates to the difference between the piccolo and the flute that we heard in the beginning of the class. A piccolo is much smaller instrument than the flute is, even though they have basically the same anatomy, they have the same kind of keys. Just because the piccolo is a lot shorter, it makes the wavelength is smaller, so then it'll have a higher frequency, resulting in a higher pitch. And we heard that in the video. And then the last one is there will be a higher pitch in the column of air where both ends are closed than there will be in a column of air where only one end is open, if everything about the air columns are equivalent, meaning the temperature and that kind of stuff remains the same, then changing if it's open or closed is going to affect the pitch. This is the reason why in the last video that we saw, when a clarinet is considered to be closed on one side and open on the other, you can create noise sounds that are much lower in pitch than a flute, which is considered to be open on both sides. So make sure these key points are in your notebook. So for the remaining of class, you are going to complete the exit ticket that is in your classwork document. It connects everything that we've talked about today. So if you have any questions, you can take this time now to ask your teacher. Make sure you upload everything to your Google Classroom and hit submit. I hope you have a great day.